Yeah. Hello, everyone. So, I think let's start the discussion. Yeah. Good afternoon, esteemed panelists and participants. We are happy to have you join us at the launch of our webinar series, and this is the second part of the webinar series. So, my name is Yasraj Gore, and I am a project manager at MPN Systems. We are primarily based out of Mumbai, which with key offices in Delhi and Goa. We specialized in the energy and environment sector, while our expertise spans electricity regulation, clean energy access, water resources efficiency, and sustainable mobility. So, since our inception in 2012, MPN system have developed a strong professional proficiency in the electricity regulatory environment, particularly addressing demand side management side of it. So we have been privileged to support electricity regulators across the country in policy making and tailoring DSM initiatives for discoms. So more recently, we have supported the MERC in notifying its demand flexibility and demand side management regulation. So this webinar series is intended to explore the opportunity and challenges in flexing the demand of a few select and use consumptions. So that can be basically ramped up or ramped down selectively to optimize renewable energy uptake. So I think before we delve into today's discussion uh, on our topic is meeting cooling demand in building via buildings via flexible energy services. I would like to quickly introduce our panelists who have joined us. Just a second. Okay. So we have Mr. Alvin Jose, who is the head of energy transition planning and energy efficiency at SEforALL. And Mr. Alvin is a clean energy specialist with an impressive 17 years of international experience working with UN agencies, governments, and research institute on sustainable energy and environmental initiatives. His experience in energy transition planning and efficiency will bring valuable insight into our discussions today. So next is we have Dr. Vishal Garg, who serves as university chair professor and director of the Indorama Venture Center for Clean Energy at Plaksha University. So with a PhD in energy from IIT Delhi, Dr. Garg is a leading expert in energy efficiency and smart buildings. So he's also a lead author of a workbook on building energy simulations, making him a thought leader in the field of sustainable building design and energy optimization. So next we have Mr. Ashish Verma, who is a General Manager, Technical Development at Tabreed India. So Mr. Verma is a specialized in HVAC systems design and execution across multiple sectors, including green buildings. So he has extensive experience in delivering international mega projects across the countries like US, Canada, UK, Russia, etc. So his global expertise in cooling solution and green building technologies will add significant depth into our conversation. So and last not but the least, I would like to introduce our moderator for today's session, Mr. Sekhar Kadilkar. Is a senior project advisor with MPN Systems. He has over 35 years of experience in the power sector in the areas of generation, transmission, distribution, and energy management, and especially in demand side management. Yeah. So, briefly, I want to talk about demand flexibility concept and importance of cooling demand in managing grid operations. So this is the flow of my short presentation. So in the historical trend, we were having a load following generation, which mainly means that you have the fixed demand, and you have the generation capacity which need to be modulated according to the demand which is there. So the demand is constant in the earlier scenario, but now you have a lot of renewable energy capacity into the grid. So so your generation is kind of a fixed because your irradiation and wind speed is can't be modulated as per your demand. So now you need your generating power plant to follow the generating power plant your demand to follow your generation, because generation will be largely fixed because of uh, environmental factors. So here in demand flexibility, what we talk about is demand response, as in you are modulating your demand as per your generation requirement, and you will also shift some sort of your demand to from the non RERs to RERs. So that's how you are able to manage your grid. So that's a main concept behind this demand flexibility conversation. And I think MERC is have had taken a lead into this, and they have came up with the demand flexibility and demand side management regulation recently. And the key aspect in this DF regulation is you have your portfolio obligation for the distribution companies, where you has to have some sort of flexible demand correlate to your previous year's peak, and Discom has to design a program to aggregate aggregate the demand which can be flexible, and actually demonstrate how you will actually demonstrate it from the non-peak hours to peak hours. Yeah, peak hours to non-peak hours. And in the regulation, you also have they also have the incentive and penalty mechanism to uh, streamline this DFP obligation. So now we came to our topic for this webinar. So here you can see the different demands for from the different consumers, and the study shows how your cooling demand will impact the overall load curve, which is basically come from the residential side. So your total load will be 650 terawatt hours of load in 2040. And you can clearly see the difference of 200 megawatt between your lowest daily curve to highest daily load. So that is significant to manage the grid, and this is mainly because of your sales will be going to increase due to different factors like environmental temperature increase and GDP growth rate and all. So your air conditioning sales will be going to increase, and that's how your cooling demand will also going to increase in near future. So this is the type of cooling demands where you can clearly see the space cooling is a major chunk of different type of cooling demand, where you need some sort of interventions. So from the in the refrigeration side, you can have the energy efficiency where you can reduce some sort of demand, but in the cooling side, you should have to be both the interventions like energy efficiency as well as the demand flexibility. So here we will talk about three different scenarios in which we will utilize the thermal energy storage and demonstrate how you can shift your cooling demand to off-peak hours. So in the first scenario, you can see that in the green line, you have your cooling load, and the chiller is basically supplying the required demand in this, which is very like it is based on the cooling demand and you are supplying it accordingly. But in the scenario two, we can see that your chillers will be operational in the non-peak hours, where you store your thermal energy, and utilize it across the day, where you will provide your uh, additional support from the thermal energy storage and reduce your load requirement. And in the peak time, you completely use your thermal energy storage so that you won't have the burden on the grid. So that is how you can flatten the load curve. But in the third scenario, we are showing how you can just support the grid without flattening the load curve. So here you have the cooling demand chillers working in the off-peak hours and storing the thermal energy and utilizing it in the uh, peak hours. So that is in mainly in the evening hours. So similar to today's conversation, we also had our previous webinar on public water works, demand flexibility in public water works, where we went into detail about how the flexibility can be achieved. So similarly, you have a cooling storage facility where, which is mainly cold storages, where you can shift your demand significantly, and you can also intervene in the electric vehicle charging part of it, where you have managed chargers where you can modulate your demand accordingly. And of course, the heat pump, which is basically you are also reducing your load and also shifting your load uh, while you are centralizing your system and also providing the shifting opportunities in it. So yeah, I don't want to take much time in this because our panelists will be going to discuss in detail about all the technologies and what kind of interventions can be required. So I'll stop here. And before we dive into our panel discussion and technical presentation, I would like to invite Mr. Alvin Joshi to set the context for today's session. Over to you.
Thanks a lot, Yashraj, and many thanks to MPN Systems for inviting SEforALL to today's very important webinar. And I think as we are all now slowly heading into the summers, this is going to be becoming more and more hot topic to talk about, no pun intended there. In a way, for those who don't know what is SEforALL, I would like to maybe spend a minute of time to introduce SEforALL. Sustainable Energy for All is a UN-hosted international organization. We are headquartered in Vienna with some country offices. And we are essentially an organization that was set up to ensure that SDG 7, which is ensuring that there is universal access to electricity or energy, doubling of renewables. At that time, now it's tripling, and doubling of efficiency happens around the world, and ensure that everybody gets access to such sustainable energy. And since then, we have been working on across various advocacy elements, but more recently, we have been more providing technical assistance and implementation support to developing countries around the world. And we are very proud to be part of a lot of the work that is happening in India. We worked a lot with the Government of India during the G20 India presidency with the Bureau of Energy Efficiency to bring forward the doubling of energy efficiency championship at the G20 level, and which was featured also in the New Delhi declaration statement. And since then, we have been really looking to see how we can go ahead and support energy efficiency uptake in the country and around the world. And for us, or the way we look at demand flexibility, it's basically a fulcrum of ensuring that doubling of energy efficiency is the route to tripling of renewables. And maybe for this, I would like to pick a few numbers and why it is demand flexibility, in our opinion, is going to be a very key aspect in the coming decade, not only for India, but around the world. Across the G20 countries, you're looking at a base load, more and more shrinking of 50 to 60% now, and there's more and more peak demand coming in. This is due to various factors. Of course, one of the key factors is climate change and more warmer days that you can look into, especially in those intertropical countries, and not to forget about the winter load, heating load that is happening in the colder countries. So you're looking at countries, for example, the US, are looking at a base load of almost 800 gigawatts going up to almost 1,500 gigawatts. You're looking at India, where the peaking is coming to around 250 gigawatts in the country. Now, this we see as a problem that will be only increasingly going to get more and more as we go into the future. As the world becomes warmer, we are looking at more cooling demand, at least at an average of 3 to 4% coming in annually with every degree of increase in the temperature. Now, this is again exacerbated by a few other good things that are happening, but it's a perpetual challenge. Is that more and more renewables are coming into the system. Renewables are cheaper than ever before. With that, what's happening is that the way renewables, especially solar loads, during the day is coming in, but the peaking is happening due to cooling, specifically if you want to see over here at evenings. And so there's a big mismatch. And then you're looking at big ramp up needs that are happening, and it's putting a lot of pressure on the capacity markets. It's putting a lot of pressure on spot markets and day ahead markets as well. At least in India, we see that if at the current rate, at least 100 gigawatt more of ramp up requirements is going to come up, and ramp up at this stage, we are basically looking at gas. So we do see that, and at the same time, you're looking at a large amount of renewables coming into the system, where during the day actually it has to be curtailed. And it's so you are looking at a lot of mismatch, seasonal mismatch, daily mismatch, and it's becoming more and more complex for the power sector and the markets to kind of match the demand and generation, as Yashaj mentioned, that ideally you would like the generation to follow the demand. And we think that demand flexibility time is now. And I think the faster policies, regulations, technologies are able to be aggregated and deployed in India. I think India can really see this challenge as an opportunity and avoid almost 50 to 60 gigawatts of ramp up capacity, primarily in gas. And also at the same time, you're looking at providing services at a more affordable level to consumers. You are looking at almost 300 million people in India that do not have lack of access to cooling and services. So bringing in more affordable services to people at the vulnerable levels. So there's a lot of opportunities that demand flexibility can really bring in. And of course, supporting in India's fight against climate change. With this, I would like to just give this broad context on why we think that demand flexibility is super important. And especially in the cooling segment, I think whatever India does will be the torchbearer for the world around to look at. So everybody is looking at a lot of interest and hopes to what India will be doing. So with this, I once again thank all my panelists and everybody who is joining us in on this conversation, and looking forward to hearing from our experts. Thanks, everyone, and Yashraj, over to you.
Thank you so much, Alvin. So, yeah, so I'd like Shekhar sir to Shekhar Khadelkar sir to make a opening initial remark, and we can start with the panel presentation.
Yes,
Thanks.
sure. Yes, Raj. Thank you. Good afternoon, all the present members. I hope some of you are also from DISCOMs. So I have been working at Tata Power for many years, and I have recently, a few months before, I have retired, and I'm working on few different projects. About my brief introduction, I had worked in generation, transmission, distribution, as well as power purchase, EV charging, solar net metering, rooftop solars, and important part of my work was in demand side management. The demand side management actually was initiated in Maharashtra in 2007-8, when there was tremendous power shortage and a lot of people were suffering because of extreme high cost of power purchase during that time. So at that time, MERC, the regulator over there, had requested all discoms to come forward and start demand side management. So what is demand side management? So we are always used to manage the supply. So whatever is the demand, we will manage the supply. So we will bring power from somewhere, we'll do something, but will not hurt the demand. The demand will remain there and we'll keep on managing the supply. And that was the philosophy all over, because since we are sellers of power, we are not supposed to save the power, we are supposed to sell the power. That was the thought process behind that. But still, world over, the demand also is another part of the load, where if you can curtail it as per your need, tremendous benefits can be achieved. So that was demonstrated at California and several other states. And through that, the demand side management initiative started. Further, they enacted regulations. A few pilot programs were rolled out. I had myself rolled out several demand side management programs. One of them was thermal energy storage program and demand response program. And therefore, I have been advised to be moderator for this webinar today. So at that time in Mumbai, that time was around 15 years back in 2010-11. We had rolled out one thermal energy storage program, and we could enroll around 6 plants across Mumbai. Few of them were in Bandra Kurla complex, few of them in other distribution areas. These were large commercial complexes or 5-star hotels, which on their own they were trying to use the thermal energy storage. However, there was no proper guidance to these guys, as well as there was no proper incentive for them to run these plants. So even though after making the plants were completely idle or were being run inefficiently. So we took one program and we started advising them how to restart these plants. We provided certain incentives, certain rebates through tariff, and all the plants started working and contributing in demand response. So demand response was our another program where as per utility need, the demand was to be curtailed and customers were being incentivized. So this thermal energy storage program was with KEMS. So at that time, they were the only supplier in Mumbai for thermal energy storage. And now we have got few more options. But what I find that in past 15 years, even though there was a lot of knowledge sharing with other customers, still this thermal energy storage has not widely picked up. And therefore, I told the organizers that you have selected a correct day of April Fool Day for this webinar, because we keep on talking, but nothing happens on the field. So since I have myself demonstrated 15 megawatt load curtailment in 2010, where again at that time also Mahesh Patankar was our partner of Tata Power, and 15 megawatts we could show for 2-hour event, and which we continued for 10-15 different events. But eventually the DSM was taken over by EESL, and the utilities started just following EESL. Another thing of DSM I feel is actually was losing its, discoms were losing interest, because cheap cost power of solar started in big way. And we are able to purchase power at 3 rupees, less than 3 rupees. And therefore, the thrust on energy saving was also getting reduced, which I'm happy that now again it is getting started. And so today we have got 2 very interesting presentations. One is by Dr. Vishal Garg, who is Dean of Plaksha University and Director Indorama Ventures. And another is by Tabreed, which is a large international player in district cooling system. So both these players will be able to tell us that what on large scale, whether the thermal energy storage or shifting of load or demand flexibility is possible or not. Why the subject of demand flexibility has come is because that MERC changed their DSM regulations, and they made it demand flexibility regulations. So what is that? So their main difference is that now there is an obligation to show demand flexibility on discoms. So for the first year, it is 1.5% of the peak load. So let's say in Mumbai, there are 3 utilities, each is having 1000 megawatt peak load. Then 15 megawatts of load curtailment as per your need, the utility should demonstrate. So they will have to develop some projects which can show flexibility of load. So that will come around 15 megawatts for each discom in the first year. This percentage will keep on rising to 5% in next 3-4 years. So this is going to be a big challenge because it's obligatory. They will be penalized at 20 lakh rupees per megawatt or something, which penalty also will keep on rising. So there is a clear-cut guideline from the regulator that DISCOM must go for demand flexibility. This is different than DSM because in DSM or in demand response, you are asking just for 2 hours, I want to shift the load for some commercial challenge or some power not being available. But in demand flexibility, you can demonstrate it as per your need. Suppose you are getting cheaper power during solar time, then you shift the demand at that time. And if you are getting some constraint, transmission constraint at some point, then you can shift the demand at that time. This is a demand flexibility. The demand more or less has to be flexible. So as per DISCOM, we should at least say if your load is 1000 megawatts, at least 5% load must be, say 50 megawatts must be available with DISCOM. Whenever they want, without load shedding, they should be able to shift. That is the whole concept behind this DF regulation. So therefore, I think MPN system had arranged 3 webinars, and this is the second webinar. And over here, we are going to demonstrate how it can be done by district cooling systems of large commercial and office complexes. Few of them in Mumbai and Delhi, like Bandra Kurla complex over here. And there are several now, even residential fully air-conditioned complexes are coming up. So whether all those complexes can have a central chilling plant, which can be super efficient, and cooling can be shared to them. So, and those plants can also work on thermal energy storage. So they can shift their load as per the utility requirement. So it will be win-win for all. And fortunately, we have got 2 good presenters today. So I'd request first Dr. Vishal Garg to present. May I request Dr. Vishal Garg to present? Please, yeah.
Thank you.
I'll mute myself now. Thank you.
Thank you, Shekharji. Let me share my presentation. Just one moment. Okay. So is the presentation visible?
Yes, sir.
Make it
But
full
your,
screen.
Yes. Is it full screen now?
One more thing is possible, but it's okay. We are able to read.
Okay. Now?
Yeah, that's good. That's good.
Okay, perfect. So yeah, thank you. Thank you. And I would be talking on how we can decarbonize the residential air conditioning energy consumption. That's the focus of our research. And we are doing some experiments. I'll share the information about those experiments. So basically, Plaksha University, we have Indorama Ventures Center for Clean Energy. And at this center, we are doing research on various aspects. And one of the important aspects is decarbonization of residential AC energy consumption. I need not spend too much time on this. We already know that the peak nowadays is shifting from daytime to the nighttime. Here is a load curve for Delhi, and we can see that the peak is happening in the night. And this is due to the residential air conditioning energy consumption, energy load, AC load that is leading to this peak. So basically, as already discussed, how we can use thermal storage and charge that thermal storage in the daytime when renewables are available and reduce this nighttime peak, which is coming mostly from the regular coal-based, oil-based, or those kind of energy sources. So for this, basically, the first thing is why thermal storage and why not battery energy storage? As of now, the battery energy storage is expensive, and it is not 100% environmentally friendly uh, as compared to thermal storage, where we can use probably we can use water and ice, which is hardly any cost. We just need a tank to put the water, which converts into ice, as well as very little or no environmental impact. So our research is currently focused on evaluating and comparing thermal energy storage as compared to the battery energy storage. So in residences, it is very common to have air conditioners, like split air conditioners or window air conditioners, and generally we'll see every room having an air conditioning unit. So the first thing we tried to understand is what will happen if we have a district cooling for residential building. And we did a case study in Hyderabad. This is the picture of that project. It has about 400 flats. The total cooling capacity of indoor units is 4,000 tons. So if I aggregate all this and put a central chiller to supply to all the indoor units being 4,000 tons, what would be the peak load or the size of the chiller? In conventional case, if it would have been split air conditioners, for every ton of indoor unit, there would be a ton of outdoor unit. So that means it would have required 4,000 tons of compressing power. But in case of aggregated load, to our surprise, instead of 4,000 tons, the requirement was less than 400 tons. So there is a reduction, a substantial reduction in our installed capacity. And this is very obvious once we analyze this data. Not all the air conditioners are running in the night. So if somebody has 4 bedrooms, maybe 1 bedroom is being used, and dining, drawing, these rooms are not being used. So it can easily come down. Not everybody uses air conditioning. Then there would be some people traveling, but then there would be some guests. So it kind of balances out. And the split ACs will not have 100% duty cycle. They will switch on and off. So here, if we are just doing centralized air conditioning, I mean, doing a chilled water system, then the installed capacity can come down by 10x. Then we had collected data for this complex, and this is what we found as the daily requirement of thermal energy in the peak month. And here you can see the peak was around midnight, and it touched about 340 tons. And we have this data for 3 years, and it has never crossed 400 tons. So what is the benefit of district cooling in a residential space? It definitely leverages the diversity. So low installed capacity will suffice. And then it improves the building space utilization. You don't have these hanging outdoor units everywhere. It can reduce the emissions. There would be less refrigerant use, so less leakages and proper control of the equipment, more reliability, a lot of flexibility in terms of, so the enjoying diversity and providing flexibility to all the spaces. And it can also lead to cost savings, not only in terms of capex by reduced chiller size, but it can also lead to reduced opex because it is operating at a very high efficiency. Now, so we realize that yes, reducing, putting a district cooling kind of a system in residential can substantially bring down the installed capacity of chiller. Now we shifted our focus to what will happen if we provide a thermal storage system and shift or the charging of the thermal storage to 100% daytime. So we took this hostel at Plaksha University. This is a G plus 10 floors hostel. It has 220 rooms and the total conditioned area is 3,870 square meters. It can accommodate about 440 students. We simulated the hostel building as per the construction materials and as per the build uh, as built drawing. And then we found that this is how the cooling load changes throughout the day. The peak load comes at around 7 o'clock, 7:30, when students are back into the hostel and ACs are on. Uh, During the daytime, they are in the classrooms or the labs, so the air conditioning utilization is less. Uh, so what we found that the peak requirement was 127 tons, and the total energy consumption on a peak day in a year would be 1750 ton hour. Out of this 1750 ton hour, the consumption in the evening and the night time, we are calling that as non-solar hours. Uh, that is about 11 hours. Uh, that's about 1600. And in the daytime, the consumption is about 150 ton hour. So the idea is that how do we shift this 1600 ton hour from nighttime to daytime by charging thermal storage? So if we go for business as usual, then we need 127 ton hour. We need 127 ton chiller. But when we go for utilizing the energy available in the daytime for 5.5 hours, and we have to charge 1750 ton hours, then the chiller requirement becomes 318 ton hours because this chiller should run only for 5.5 hours and generate 1750 ton hour that is required in the night time. So we can see that the chiller is of 127, it becomes 318. And if we want to freeze ice and we have to go for negative temperature of -5 degrees centigrade, then the derating happens and we need to further increase the chiller to 400 tons. So you can see that as compared to a regular chiller, there is much higher chiller capacity required if we want to charge the ice in the daytime in 5.5 hours. So that is the chiller we installed, and it can work in 3 modes. It can be in a mode where it is charging the tank. It can be in a mode where it is directly supplying cooling to the building without charging. And the third is it is discharging the tank and providing cooling to the building. That will happen in the night time. So we have this system and it is being commissioned. And now we are trying to understand that how much nighttime load will be there on running the pumps and the indoor fan coil units and fresh air system. And we are designing a battery which will store this energy also from the energy generated in the daytime, so that the nighttime air conditioning load is 100% stored during the daytime using renewables. So this is the sizing of the photovoltaics. We need 400 kilowatt peak of photovoltaic system, which will generate enough energy in the daytime to not only charge the thermal storage system, but also the battery electrical storage system, battery energy storage system. And that means overall nighttime air conditioning consumption would be 100% shifted to photovoltaics. So here you see what our thinking is that if this kind of a system is deployed to a residential complex, then there would be a possibility that we have less capex because of the reduction in chiller. We have a less opex because it is efficient, and the photovoltaic based energy is much cheaper than the grid-based electricity in the night time, so it can save cost even when there is a loss of efficiency in charging and then discharging, as well as loss of uh, efficiency at the chiller also, because it is delivering at -5 degrees centigrade. So even considering all that losses, because of the better tariff coming from the solar energy, in the end, it will give lower OPEX and it will be 100% green. So this is what we are trying to establish in this lab. This lab is an open research lab, meaning hereby that anybody, if they want to do any experiments with different type of thermal storage material, different algorithms, or whatever, if somebody wants to try out, then it's a lab available for researchers, for uh, industry, for policymakers, even startups. And here are some photographs of the left-hand side is the tank, right-hand side is the chiller, heat exchanger, and pumps, etc. These are some of the experiments that we are planning in the setup. We will try to analyze the load patterns and then try to see how they vary over the seasons. We also want to do some behavioral studies where we want to charge the occupants in the hostel as per the actual air conditioning consumption and see if it leads to better AC utilization and reducing the energy consumption. We, of course, would like to evaluate the overall system efficiency, taking into account the losses in charging and storage. We like to see the performance of other phase change materials. And we like to develop a forecast model for how much storage is required per night, because it's not a good idea to charge more and not use it, and also not a good idea to charge less and then there is a shortage of capacity. So overall, a lot of experiments are planned to reduce the overall OPEX at the campus level by utilizing various energy sources and deciding when to charge the batteries and the thermal storage, when to discharge them, and decarbonization as the fundamental goal here. So that's it. That's what we are doing. As a research center, we are more interested in doing research and showing what is the overall performance so that we can take a better policy decision here. We can also bring this data and bring this learnings to the industry and help them, develop systems and implement them. Thank you.
Thank you, Doctor. Very interesting presentation, a lot of experiments. Somebody has to do such experiments to really demonstrate the people that it is viable and it works. Before taking any questions, I will go for next presentation, and then if any questions are there, later we will take. Thank you, Dr. May I request Ashish Kumar Verma, General Manager, Technical Development, Tabreed, India, to give his presentation. And this is also going to be a very interesting presentation. It is on district cooling, which is a need of the hour. Large complexes, industrial, commercial complexes are developing, which are fully air conditioned. Huge data centers are coming up across the country, which need extremely high air conditioning. And I think Ashish, who has got international exposure to several plants, they have already installed several plants across world. So this presentation, I would request everybody to give due attention. Over to you, Ashish.
Thank you so much, Mr. Khadilkar, and my pleasure to be here today. And thank you, Dr. Garg, for such a nice presentation and demonstrating how district cooling can be integrated into the residential sector and how solar or renewables could also be integrated into the same domain. So I'll start with my presentation. So can you just confirm if my screen is visible and I'm audible?
Yes.
Yes, yes.
Okay, thank you. Okay, so like what Yashraj started with and explaining about demand flexibility, which is something very, very critical now, considering whatever we have been witnessing in our country, the peaks which are kind of, doing records after records. So that is very, very important to discuss. And we will just discuss why, and because since the theme of this session is on cooling and why cooling is important for demand flexibility. So I'll just touch base upon that. Start my presentation. Before going into the specifics, I will just quickly touch base on what is Tabreed, because maybe there might be people who might not be familiar with Tabreed. So basically, we are one of the world's largest cooling utilities, mainly operating into district cooling or the cooling market. We are headquartered in UAE, Abu Dhabi. We are currently operating 92 plants in 6 countries and delivering over 1.3 million refrigeration tons, which is helping us in saving 2.6 billion kilowatt hours of power, which is also helping us in eliminating 1.6 million tons of CO2 emissions. You can see on the right side, the iconic installations where we provide our cooling services, whether it is Burj Khalifa in the Dubai downtown or the Ferrari World or the Sea Worlds or the Abu Dhabi area. So these are a lot of iconic installations where we provide our district cooling services. Our primary shareholders are Mubadala, which is Government of Abu Dhabi's Sovereign Investment Fund, and ENGIE, which is a French utility giant mainly into energy and district heating and district energy. In India, we are present through a platform called Tabreed Asia. It is headquartered in Singapore, and we have Tabreed and IFC as shareholders here. So Tabreed is 75% and IFC is 25%. IFC is World Bank group, which is mainly into financing for sustainable measures and mainly lending out to private players. And Tabreed India is a subsidiary of Tabreed Asia. To start with the need of cooling, why cooling is important and why are you even discussing this topic, right? So if you see the curve on the left-hand side, you can see that in 2023, we witnessed 1.46 degrees C temperature rise above, the pre-industrial levels. And what we have been discussing that we need to limit it to 1.5, so that is gone. So we are already very close to 1.5, or in fact, we already breached it. So now the focus is that how should we limit it to under 2 degrees? So this is the race now where we are struggling. And this shows the importance why cooling is important, because people are getting exposed to such high temperatures now. If we talk about India, this is the climate map of India, where you will see that we have 5 climate zones. And the majority of India is covered by the top 3. That's hot and dry, warm and humid, and composite. And all of these 3 climate zones need air conditioning for most time of the year. And that's why cooling is very, very important. Cooling can be in any form. So there are different types of cooling things. Maybe there could be, the most simplest thing is the ceiling fan or the smaller fans. And then we have desert coolers, and then we have the air conditioning systems. So those we call that as a refrigerant-based cooling systems. When we have this kind of a temperate tropical climate in India, so we have our own issues with respect to cooling now. There have been enough studies, and there have been recent reports also. Maybe the most recent was by the World Bank, which says that India is most likely to be one of the first place in the world where we are going to experience heat waves that can cross human survivability limits. So, and this is very, very serious thing. And we all know, due to this temperature rises and all the heat wave effect, there's a associated productivity loss, which can render people jobless. And this is just the tip of iceberg, because see, if you see the third bullet point here, so in India, mere 8% of Indian households need own air conditioning, and this is very, very low as compared to other countries. So if we assume that this 8% increases to 20 or 30%, then you know how much will be the power demand required for cooling, and that's why it's very, very important. In fact, in India, we have one of the lowest per capita energy consumptions for space cooling. So it's only 69 kilowatt hours as compared to a world average of 272. And it's almost 1,000 for developed countries like America. These are the statistics where there is a demand for a new air conditioner every 15 seconds. Maybe this is forecasted for 2037. And this all is led by our tropical climate, the low penetration of air conditioning, rapid urbanization, and the rising per capita income in the country, and the rising population. So we are estimating the space cooling capacity might reach 268 million refrigerant tons by 2030. So this is a very big number. And it is going to be like, we will be the fastest growing cooling market in the world. And this has been demonstrated in multiple research now. A very good thing what we did was we came up with an India Cooling Action Plan, which was published in 2019 by the Ozone Cell of Ministry of Environment, Forest and Climate Change, supported by various other stakeholders. It paved a path for us, what needs to be done because of this growth, which is anticipated in cooling market. So there were certain technologies which were recommended, and district cooling was one of the technology which was recommended in this India Cooling Action Plan. Let's see where do we stand in terms of renewable power generation. So we are just comparing right now solar and wind. So from 2017, 2018 to 23, 24, you see every year there is an increase. We are adding a lot of renewable capacity here, and it's increasing like from right now it's like 29% of the total power installed power capacity. Now, if we compare this renewable power, which is comprising of wind and solar, with our cooling demand, where do we stand? If you see the right bars in blue, you see that our cooling demand, and that's only for space cooling. I'm not talking about other sectors like cold chains, transport, cold chains, other areas, but it's only for the space cooling. So year on year, the demand for space cooling is more than the renewable power we are adding in the market. And this is something very important to notice. If you see the graph on the right-hand side, if you remember, we witnessed 250 megawatt of peak energy demand last year, May of last year. And space cooling was only contributing around 10% there. So the demand for space cooling was only 25 gigawatt. Now, the forecast is that by 2050, the estimated peak energy demand for India would be somewhere around 700 gigawatt, and space cooling will be contributing 45% to that. So see the jump from 10% to 45%. And this is a very big number as far as air conditioning is concerned. And most of the air conditioning market or this demand is coming from residential sector, which is mainly fed or catered by the room air conditioners, whether those are window or split kind of things. We will just understand how district cooling can be leveraged for demand side management, what we have been discussing in this webinar. I will start with a little bit of basics. Like I mentioned earlier, the simplest form of cooling equipment is a fan. And then it becomes, we have the desert coolers. Those are all non-refrigerant based cooling solutions. But right now we will be focusing mainly on the refrigerant based cooling solutions, which start with a simple system window and split, which is the most commonly used right now, and mostly in the residential sector. Then we have slightly bigger equipment. We have VRV, which is a very variable refrigerant volume, which is again a DX system. A DX system means directly refrigerant is used for the cooling. There is no secondary medium. Then we have the air-cooled chillers. Air-cooled chillers are utilizing a secondary medium, mostly that is water. Slightly bigger equipment will be comprising of the water-cooled chillers, which are of bigger capacity as compared to air-cooled chillers, bit more efficient than air-cooled chillers, but they need additional component, that is water. So because there is a cooling tower which is attached to a system which needs constant make of water for cooling. And at the last end of the spectrum is the district cooling system, and which is by far, if you can see, the efficiency is best out of all what we can see here out of the refrigerant systems. So this is the impact district cooling can have in terms of efficiency. We'll learn more through examples in the coming slides. Before going to that, I will just explain what is district cooling system. So district cooling is not a new technology. It has been existing since long time now. It has been existing in Middle East, America, and other parts of the world since long time now. Mostly it was used as district heating, but hotter countries like the Middle East need cooling. That's why it's more popular there. So district cooling is nothing but a centralized production and distribution of cooling energy. And mostly the cooling energy is in the form of chilled water, and that is distributed to a network of building through a network of insulated pipes. And mostly these network of pipes are underground, which are connected to the district cooling plant. I'll just use my pointer here. So if you see on this image, this is the district cooling plant, which is sitting remotely to the buildings to which it is serving. And these are multiple buildings which is catered by this single plant. So this cooling plant is generating chilled water, which is somewhere around 4 to 5 degrees C, and then it is pumped to the respective buildings. In the buildings, there is a small equipment that's called ETS, Energy Transfer Station. It is nothing but a plate heat exchanger. On one side of the plate heat exchanger, it is the chilled water coming from the district cooling plant. And on the other side of the secondary side is the building level chilled water system. So basically, we are segregating both the chilled water circuits, building side and district cooling side, so that there is no mixing of the fluid. In case there is a issue at the building level, it should not impact the district cooling system as a whole, because reliability is very important for district cooling plants because multiple customers are being served. So building will have their own internal chill water circuit, which will be circulating chill water to the respective air handling units. Air handling units will be having the warm air coming from the air conditioned space, getting cooled and returning back to the space. This internal water circuits gathers heat from the air, and then it delivers heat to this energy transfer station. And from this energy transfer station, the warm water returns back to the district cooling plant for further recycling and further getting recooled. So this is a simple process how district cooling plant operates. And there are multiple components here. The major component is the chiller, which is the major equipment which provides or generates chilled water, which is the cooling medium. Chillers are associated with cooling towers, which is a medium to dissipate heat into the ambient, because the heat what is gained from the buildings had to be dissipated somewhere. And that heat is going into the environment, which is happening with most of the air conditioning equipment. They are gathering heat from the indoors and rejecting it to the outside world. A major component of the district cooling plants is the thermal energy storage tanks. So thermal energy storage tank is what Dr. Garg spoke about. So there are multiple types of thermal storage tanks, which I will just cover in the next slide. So mostly the purpose of these tanks is that they store chilled water or ice during the off-peak hours. Off-peak hours when the electricity tariff is on lower side. And then it is used when there is a peak hour. So it helps reduce the peak of peak power consumption for the cooling plant. Very quickly, I'll cover these energy storage tanks types. So the first and foremost, the most commonly used tank is the stratified chill water storage tanks. And these tanks are used in almost all of our district cooling plants. And it serves two purposes. Firstly, it helps in moving the peak from the peak duration, so shaving off the peak load. And second advantage is the redundancy. It provides a redundancy because in case there is an issue with one of the chillers, this tank could be utilized to provide cooling. So it has its own principle of operation of thermal stratification, and that is based on the density difference of hot water and warm water. And these are specially constructed tanks. The left-hand side is the regular thermal energy storage tank, which is used in the district cooling plant. And the right-hand side is a smaller tank, which is mostly used as a backup kind of thing, mostly in data center kind of industry, where they need backup in case there is a power outage and chiller goes down and the DG has to be started. So there's a time lag. For that particular duration, these smaller thermal energy storage tanks are used. Another form is the ice-based thermal energy storage tank, where these are the balls, plastic balls, where there is a material inside. Mostly it's water or a salt solution. So the water is sprayed, or the brine or the salt solution is sprayed over these balls, where inside the ball there is a water. Water freezes and stores energy in the form of latent heat. And whenever we need cooling from the thermal energy storage, this ice starts melting and provides cooling for the requirement. And nowadays we are having multiple generation of these ice-based thermal storage. Now the newest generation is having this ice air capsule here, which helps in expansion and contraction as the ice is formed inside the ball. Another form is a phase change material, which is in between the chill water thermal energy storage tank and the ice-based system. The advantage of PCM is they occupy lesser space as compared to chilled water, but they have limitations in terms of the temperature at which they can operate. So there are two types, negative and positive. I will not cover it here right now. I will just explain how district cooling is helping us out in terms of reducing our power demand. So we are taking an example here. There's a 20,000 RT cooling demand, and there are two systems where we are comparing. Top one is the district cooling system, and the bottom is the decentralized system, that is a standalone cooling system where each building will be having their own independent cooling plants. When we go for a district cooling system, we definitely have an advantage of demand aggregation, and that helps us in having better diversity. So we have assumed a diversity of 80% here. So instead of like 20, to meet this cooling demand of 20,000 refrigeration tons, probably we can install a capacity of around 16,000 tons because of the diversity benefits. If we couple a thermal energy storage tank also, the capacity will be 2.5 KRT, that is 2,500 refrigeration tons. It helps us in reducing, first of all, the mechanical capacity of the cooling plant. And your power consumption is only for the mechanical component and not for the thermal energy storage and the power demand, sorry. So when we consider a peak electrical efficiency of a district cooling plant, which is around 0.85, it can be better than that also, but I have considered a conservative number of 0.85, we'll be needing a power demand of 11.5 megawatt. Now, if you compare this with a decentralized system, so now mostly decentralized systems go for additional redundant equipment, which is a necessity because in case failure of any component, they will need standby equipment. And also they don't have the capacity to install TES. So there is around 15 to 20% redundancy if we consider that in the system designed for decentralized systems. And normally the efficiency varies from 1.1 to 1.4. 1.1 will be for a water-cooled system and 1.4 will be for an air-cooled plant. It is translating to a power infra requirement of 25 megawatt to 32 megawatt. And that's a huge difference if you can see. So 13.5 megawatt power savings can be achieved if we can go with a combination of district cooling plant coupled with a thermal energy storage system as compared to conventional plants. And how we are managing it is, if you can see the curves on the left-hand side. So there are three curves, so three distinct peaks of each customer or each building. So customer one could be in an office building, which is peaking in the afternoon. Customer two could be retail, which is peaking somewhere in the evening. And customer three would be a residential customer or hotel, which will be peaking probably during the night time, 9 or 10 in the night. So here, that's the reason we are able to manage all these peaks, because we are aggregating the demand here to a district cooling system. And how the thermal energy storage tank works is like, this is the bell curve, which follows, every load pattern follows this curve. So this portion above this horizontal line is the peak, what is needed for the peak time. So what district cooling and thermal energy storage system does is, this hatch portion is the time when we charge our thermal energy storage tanks, and we utilize it during this peak requirement. And that's why we are able to provide to the cooling demand of the peak time utilizing a lower capacity equipment. So this is the benefit what we can get with the thermal energy storage system coupled with a district cooling system. District cooling can also help us in enabling circularity, which is a very important subject nowadays, because we have to be having circularity in our resources. And the statistics are like only 7% of material in the world are being recycled, and this is something which we have to focus upon. And district cooling is a very good medium where we can integrate all the technologies and we can recycle the components. There are multiple options how we can do it, but before that, what's normally being done is we have to first reduce the demand. We can always install 20,000 tons, 30,000 tons, but we have to obviously optimize the demand. So what helps us in optimizing is the passive design on the building when the building is being designed. There are passive measures including green building measures, which are being incorporated, which helps us reducing or optimizing the cooling demand for a particular building. And when the demand is optimized, then we go for district cooling integration to supply the cooling. For district cooling system, there are multiple avenues which could be integrated. The first is solar energy. We heard from Dr. Garg how solar energy was integrated into the cooling system. We can also integrate wind energy. We can also integrate waste to energy plants. Seawater cooling is something very, very, we have done one plant. I have this example on the left-hand side, how seawater cooling operates. Then obviously the water storage, whether it is thermal storage, chill water based or ice-based storage or PCM-based. The most important integration of district cooling is the utilization of treated sewage effluent. This sewage STP water, when it is treated, normally it's discarded. If I give you example of Middle East, it's normally discarded. And district cooling plants can utilize this water, which can help us reducing the dependence upon the potable water or the fresh water. District cooling system can also be integrated with a combined heat and power systems, a cogeneration or a trigeneration plant, which is in fact one of the recommendation of the ICAP. And one important thing what we have done recently for Tabreed is we have recently commissioned a geothermal plant where we are providing cooling through a geothermal system. And we are utilizing hot water. We are generating hot water through geothermal means at 90 degree and operating a vapor absorption machine, which is very different to vapor compression system, which is conventionally used. And that's how we can integrate all these systems. But this is not at all possible when you talk about standalone buildings or standalone cooling plants, which are in the middle of downtown, middle of the city. Sea cooling water is very important in terms of how we design it, because it will have an impact on the marine life if it is not designed properly. For example, the intake is from a bottom level. We see the temperature difference as per the level here. So it's 6 degree at the bottom. We take the 6 degree water, and then it is discarded after utilization through a titanium heat exchanger, because seawater and the normal water cannot be mixed because it is corrosive, obviously. So we have a different metallurgy here. So titanium heat exchangers are used, and the hot water is discharged at a depth where it is equal to the sea temperature of the same 12 degree. So this is how the systems are being designed, and we have an operational plant in Bahrain where we have the seawater cooling there. There are other sustainability advantages of district cooling for end customers, like there is 40 to 50% lower power consumptions. We have 30 to 40% lower carbon emissions, 15 to 20% lower cooling cost to the end users. And it also improves the building space utilizations, because your basements, which were otherwise used for the cooling plants, would be now free for better usage. Also, the terraces, which were probably would have been used for locating cooling towers, could be utilized for better purpose. Maybe you can go for more solar generation. We can go for terrace gardens and other aspects. There are other hygiene factors also related to district cooling. So reliability is very important, like I mentioned earlier. So reliability is in the range of 99.7%, more than that. We discussed how the peak is clipped using thermal energy storage, and then we have flexibility in capacity design and installation depending upon the location. And all the buildings are very quiet and visually appealing, because you will not have this noise producing equipment inside the buildings or all those outdoor units located in the buildings. A very important feature of district cooling is how to mitigate the urban heat island effect, which is very prominent in our urban centers. So if you see the graph on the left hand side, if you see the rural area, how the temperature is rising from rural where it is around 30 degrees C, when you go to the downtown, it is increasing by almost 3 degrees C. So this is the impact of urban heat island effect, and district cooling can help mitigate this kind of phenomena, because district cooling plants can be located away from the downtowns and at a more remote area. Another important thing to note here is that when the temperature in the ambient increases by 2 degrees, there is a higher energy consumption of around 4 to 6 degrees. So whenever we are operating our cooling equipment, whether it is window air conditioner or split air conditioner in an urban environment, then definitely, because these units are normally rated for 35 degree ambient. If you see the ratings or testing mechanism, these are normally rated for 35 degree ambient temperatures, while we have been operating those for more than 40, 42, 43, whatever is the temperature in our region. And that's why they are inherently inefficient. And this is helping us in the SDGs. I'll just quickly go to a case study for district cooling.
Ashish,
Yeah,
please be a little quick. We
sure.
should close in 5 minutes.
Sure.
Thank you.
So this is a case study on district cooling. So where it's a mixed use development where we have a combination of retail building, residential buildings, hotel service apartments, and the office buildings. The estimated cooling load for this development was around 7,900 tons. And the master developer also explored if air conditioning or central air conditioning could be provided for the residential blocks. So we have two approaches. First is traditional approach where we have the individual cooling plants for individual building, whether it is central chillers or the VRV. So we considered chillers for the retail, VRV or DX system for the residential, VRV for the hotel, and the chillers for the office space. The cumulative installed capacity considering the redundancy was 8950 RT, which is significantly higher than the peak cooling load. And again, these systems have the cooling towers on the top and individual cooling system. They were relying on grid power and all those things. But the major point, if you can see here, is the power demand was 6.87 megawatt with a combination of all these cooling equipment. And the assumption was 1 kilowatt per RT, considering 85% diversity, apart from the space what will be required for installation of cooling towers and the chillers. I'll quickly go to the district cooling approach, which is normally a demand aggregation approach coupled with thermal energy storage. Compared to a conventional approach, we were able to meet this cooling demand of 7910 RT by an installed capacity of only 6400 RT, out of which 4800 was mechanical chiller capacity and 1600 was the thermal energy storage system. So when we are installing this TES of 1600 RT capacity, we were kind of shaving off the peak demand by 1.36 megawatt. This is what thermal energy storage can benefit in this kind of a mixed use development. And one more thing worth to note here is that maybe for residential blocks, like Dr. Garg gave an example where residential were, the peak was 4,000 and installed capacity was somewhere around 340. So here, if we have a mixed use development, probably we need not install even 340 because residential buildings could be catered through the equipment which is supplying in the daytime for the office and other areas. So this is one of the advantages when we have a mixed use kind of development. This is the financial impact when we compared both the systems, standalone versus DC systems. And considering upfront, first is the capital cost, because obviously the standalone cooling systems are a bit cheaper. That's why the cost is lower per RT. But DC systems are costlier per RT. But when you consider the high side capex here, the DC system cost is lower than the standalone cooling systems. And main reason for that is the lower installed capacity. And even power demand is 4 megawatt as compared to 6.87 megawatt for the standalone cooling systems. So when we compute the utility cost basis above equipment selections, we are arriving at a number of 11.3 rupees per RTH for a DC system versus 12.75 rupees per RTH for a standalone cooling system, which demonstrates the saving as far as operation is concerned for district cooling plant. This is the overall impact. This is just, again, the same thing. There is a reduction in installed capacity, reduction in power demand, more free area for the developer or the end user, lower lifetime cooling cost, and visually appealing buildings. We have multiple examples of district cooling. We are short on time. I'll just run through the slides now. So we have an example of Gift City in Gujarat, where district cooling is already operational. We have district cooling in DLF Cyber City in Gurugram, where our office is located. There are two tender-based concessions what have been awarded to Tabreed, Hyderabad Pharma City, which is one of the largest district cooling concession, 125,000 tons. And another is for the capital city of Amaravati, the new capital of Andhra, where the capacity is somewhere around 20,000 tons. So these were all tendered concessions which are awarded to Tabreed. One interesting case study I wanted to discuss here is quickly is there is a project what we are operating in Gaon, Tata Realty. Along that project, there are multiple other developments. If we combine the cooling demand of all these developments which are in close proximity, it was somewhere around 45,000 tons. And if the district cooling would have been planned here, we would have met this 45,000 tons of peak capacity by probably 28,000 tons of installed capacity. And these are the benefits in terms of the power demand, installed capacity, energy consumption, carbon emissions, and the life cycle cost. But we do have certain barriers where the district cooling is still, in nascent stage. So there are no policy guidelines for network or the easement for the chill water network. So this is something very, very important when district cooling has to be incorporated in master plans. There is no mandating for district cooling, even exploring or doing the feasibility study for district cooling for large master plans. There is no policy for direct power procurement by DCS utility. Then we have complications with respect to SEZ versus non-SEZ. And then again, the applicability of GST when the chill water is being supplied to the multiple customers. All these factors are covered under the regulatory landscape. So I'm just comparing here a few of the peer countries here. So where India stands, as compared to other peer countries in the region. So we're comparing with countries like Thailand, Vietnam, Singapore. Singapore, in fact, is the most mature DC market here, apart from UAE. But in India, we are still at 8% of AC utilization, like I mentioned earlier. So there's a huge scope for DC implementation. Quickly going to the regulatory levers. So we are comparing here how DC regulation is there in multiple countries here. So I'm comparing here the Singapore and Abu Dhabi, and for other European countries, mostly district heating. So first and foremost, the most important thing what these countries have done is there's a licensing thing. So district cooling provider is having a license to operate, and those only competent players are granted those license by the authorities. So those authorities could be like Energy Market Authority, I think, in Singapore, and Department of Energy in Abu Dhabi. Then the planning is made mandatory. So when you are planning for your developments there, so district cooling feasibility has to be analyzed. While Singapore mandates district cooling in certain service areas, Abu Dhabi and Dubai does not have that mandate as of now. There is a competition regulation and price regulation in both the markets. There are certain service standards, SLAs and KPIs that have to be met. Those are agreed upfront. And there are certain technical codes and standards. Those have to be complied for any district cooling project to be implemented in these countries. As far as India is concerned, may
I request, this is Mahesh Patankar. Ashish ji, can you please conclude the presentation? It's been quite some time, right? So
sure, Mahesh. Sorry about that.
We can take some questions also, right?
Sure. So this is just my last slide. So basically, there are like certain barriers of district cooling. We are trying to address how district cooling, barriers could be removed. There are in terms of planning and demand management. There are certain pre-investments which goes into district cooling because it's a capex heavy project. And there are certain payment uncertainties. So there are a lot of things which have to be done as far as regulations are concerned. I will not go into much details. I'll just go to my last slide where I'm just summarizing what is actually required for district cooling to take off in India. So zoning has to be defined in high density master plans. Licensing of technically competent providers have to be done. Feasibility studies have to be mandated beyond certain size of master plans. PPP framework have to be standardized for faster adoption. And tariff controls will follow once we have all these measures in place. There has to be a social mandate to provide subsidized thermal comfort, simplified permitting and fast track approval for the projects and land allotment. And ultimately, what is important is recognizing cooling as a utility. This is my last slide, and I'm concluding here. And sorry for exceeding the time limit.
Absolutely. Excellent presentation, Ashish ji. And I think separate discussion with you really is deserved, because several points which at regulatory level as well as for discoms, if we want to really scale the energy efficiency in cooling, this is one of the excellent presentation we are having. But due to want of time, we will directly go to questions and answers. So Yashraj, if there are any questions, or I'll ask few questions to all panelists.
Yes, sir. I think we can start with the questions. We are addressing the question in Q&A section, so you can ask your questions.
Okay. So first, I will request Dr. Garg that a lot of research is being done over there on thermal energy storage, and it is very interesting. In our experiment with thermal energy storage, several of our customers told that whenever they are running chillers at negative temperature, the chillers are losing efficiency tremendously. So whatever is quoted on the charts that efficiency is different, but the actual what they experience, that probably the chiller starts consuming double power. So what is your experience over there?
Yeah, so it is obvious. So instead of giving +5 degrees centigrade chill water, if it is giving at -5 degrees centigrade chill water, uh, so we have to have the curves of the chiller at that operating point, and the chiller selection should be done so that it is efficient at that point. Yes, we have just commissioned this plant, and the plant was commissioned by Tabreed, and we are hoping to get these measurements. But we expect about 30% loss, 30-35%. It won't be double.
Okay. Okay. But do you think any particular type of chiller, say centrifugal or some other type, which is better in running at negative temperatures?
So we now have to understand that what kind of chillers perform well at -5 degrees. Uh, I think we have gone for a screw chiller, right, Ashish?
Yes, yes.
So we have gone for a screw chiller.
In fact, we have a limitation on centrifugals running on negative temperature. That's why we have to go with screw chiller. That was something technical requirement.
Okay. And one more thing I had doubt that now we have got tremendous windows and split air conditioners, and that number is growing so rapidly. I think India is the world's fastest wrapping air conditioner market, which is growing rapidly. So these are all solutions for a very large systems of district cooling or very large office complexes. So is there any solution available for residential, say 5 to 10 TR total load of a completely air conditioner home, where any thermal energy storage solution is available? Dr. Garg, as well as Ashish, if you know, you can.
I saw one long back.
Okay.
By a US company, and it was around that range, 5-10 tons rooftop unit where they could do thermal storage. But I don't think they are still offering that solution. So it becomes quite expensive at such a small scale, I guess.
Yeah, that's a major limitation. The cost becomes too much. So we do have options available. And there's like, there are a few players, they provide, they call it heat battery or something, but the cost is prohibitively high.
Yashraj, whoever is having question, you keep on asking in between, because I have got endless questions. So we can keep on discussing. It is a subject close to my heart. So otherwise it will turn into a discussion. You open the floor for others.
If I may just ask here, yeah, Mr. Khalilkar, sorry for jumping in, but I can't resist asking this question to our colleague Alvin. Alvin is based out of Europe, and I think Europe has clearly defined the building codes in such a manner that those really promote district cooling, and the efficiency levels of most of those development, be it residential or commercial complexes, for heating and cooling both, are very high. So, Alvin, from your perspective as sustainable energy for all, and what you're seeing globally, what are the opportunities for us to influence through some sort of a policy push opportunities such as thermal energy storage and district cooling?
Thanks, Manishji. I think when it comes to, I guess, comfort temperature services, right? That's how I kind of phrase it. Because over here we have both more, actually, it'll be surprising now. I'm based in Vienna. The sales of ACs are going higher during summers here. Yeah, people are actually buying ACs over here, which is very fascinating. And heating is something that has been there in the culture itself for Europe, right? As a centralized service. So it is less of a sell. But I would say Europe is not a monolith in that this way. There are certain countries that are more, let's say, forward-looking than others. So you could, I saw Ashish mentioned about the Denmark, the Copenhagen, district cooling, and the Swedish district cooling systems. heating systems, sorry, are very well recognized around the world, actually, and the Polish ones as well. But I think uh, it is it is a bit of a challenging time right now, and we saw this during COVID time, when the gas prices really went up, right? Because of the embargo, especially with the Ukraine crisis over here, the gas prices really went up at that time. And the heating services here became really pressed in terms of costing. And there was a big push over here from the European side to move away from gas-based heating systems, be it central or at the building level, to more into electric heat pumps. And to be honest, that has not really taken up. I mean, it is really coming up, but it has not taken up to that scale that we are hoping for. Uh, so the central message is that any kind of this urban planning induced systemic change needs a lot of time, needs a lot of players to come in and agree to it, and very difficult when the system is already in place. This is the challenge. So we are looking at a lot of new types of district heating services coming up in new developmental areas, and their policies and regulations really make a sense. So I think a few of the regulations, policy recommendations which Ashish mentioned, that there needs to be a mandate for district cooling services. I think we should now go beyond this feasibility study thing, right? I think this has been happening for many years when it comes to district cooling. I think the technology is at beyond feasibility phase. I think now what really needs to happen is, in any new kind of urban expansion, there needs to be a policy push. I don't see this, to be honest, happening at a very central level. The states have to take it up. And in many ways, it is a state's mandate also at some level. So my hope is that if more and more focus can be brought up in key states, where a lot of new urban areas are going to come up, new industrial zones are going to come up, especially from a special economic zoning service, where those mandates can be put in. And these kind of tenders for concessions you're hearing as, or cooling for as a service kind of bids are taken out, where you have these zones like we see power purchase agreement, cooling purchase agreement, we basically have, and we go for tenders. I think that will be kind of a way of looking into a new market model. But looking into residential segment, I think it is still, it has some way to go to convince current urban planners to come into the mix.
Thank you so much. I
Yes,
think
yes.
all the answers, Alvin's sort of intervention, Ashish's intervention, and also Vishal's intervention was so complementary. It's really sort of music to my ears. I think somewhere we are now seeing that market transformation. But back to Mr. Khadilkar, back to you.
Thanks, Mahesh. Your inputs are always very interesting. Uh, Yashraj, do you have any question or?
Uh, yes, so we have one open question which is pending. So uh, this is question from Shreya Bansal. So in case of district cooling system, what is maximum distance that the chiller water can be transferred effectively, taking into account the loss of coolness of water being affected by outside temperature? Also, what about the cost of laying highly insulated pipe under the city? So how long will it take to turn the cost to zero? So yeah, any of our panelists can take this.
Yeah, I can take this up. So basically, this is a very relevant question. So when we have district cooling plants, our pipelines are going up to 30, 40 kilometers. So distance is not a limitation. So because the pipes are all properly insulated, and most of these pipes are going underground, where the heat gain is very, very negligible. And we are designing our pipes accordingly that the friction rate or other losses are minimized, and the pipelines are optimized in times of selection. So there's no limitation, but definitely I can say that 30 to 40 kilometers we have seen our plants. So, and those plants are working for since long time, and absolutely there's no problem. As far as the costing is concerned for the network, yes, this is one of the major factors for a district cooling plant, that the network involves a lot of pre-investment because you need to lay network while the customers might not be there. And the only way to reduce that pre-investment is we will be to install the network in phases. So whatever customers are there in the first phase, we put the network only for that phase and then expand as and when the need is there. So this is how we can minimize the pre-investment on the cooling networks. Hope that answers the question.
Yes, absolutely. Yashraj, any more questions or should I conclude?
No, I think you should
Yeah.
conclude.
Yeah, it's 5:30 already, and we had two great presentations. Mr. Alvin also contributed with international vision regarding what is happening in this district cooling and central cooling area. See, in India, we are already seeing that in large cities, the total power consumption of air conditioning has crossed 45% of the total consumption. So this is increasing extremely rapidly. Earlier, one household used to have hardly one AC. Now there are 3 to 4 ACs per household. So this is happening at residential. All commercial complexes are centrally air conditioned. So basically, there are tremendous opportunity for having energy efficiency. 1 minute. For having energy efficiency in the field of HVAC. It is there everywhere in machines, in cooling systems, in chillers, in pipelines, in the brine. Every part of the system it is not fully efficient still. In residential particularly, we are finding that very few energy efficiency measures have come in these ACs. You can't remotely switch them off. You can't give control to Discom to switch off because these are a lot of load is unnecessary load. This can be switched off during any demand response event. We don't have those controls. What has happened is only they have become inverter based. So that is why they have become at least 20% more efficient than the earlier ones. But still the gas, the leakages of gas, the environmental damage, there is a lot of things can be done in air conditioning. And as per my view, under demand side management, HVAC is the most important area where discoms as well as regulators must concentrate their attention. We can have more efficient, all the efficiency of these air conditioners is more than 1 kilowatt per ton. We have done load research and found that there are several residential as well as commercial ACs which consume 1.4 kilowatt per ton. So this is a norm because nobody is willing to replace the AC because the efficiency is going down. And that is causing a lot of discomfort to Discom as well as huge cost to the customer. So this was very appropriate webinar and addressing the point. And Dr. Vishal Garg as well as Ashish Verma, we are thankful for joining this presentation. I think Alvin has left, so I also extend my thanks to Alvin, Dr. Mahesh Patankar, and team of MPEN. Thank you very much. I think we can now close the session.
Thank you.
Thank you, Mr. Kadilkar. Thank you.
Thank you. Thank you so much.
Yeah.
Thank you, Dr. Garg. Thank you, Ashish.
Thank you.